I received several awards in different locations, but getting one at home is really the biggest pleasure and the biggest honor. So Professor Ennis already gave some introduction to those expressions that not all of you are familiar with: supramolecular entities, peptide self-assembly. I'll try in the 8 minutes that I have to tell you a little bit about the things that we do that are really ranging from things that are in biotechnology, in material science. So we span the eastern part of the campus in the sciences, but we are actually looking at the sociology of molecules, trying to understand why molecules know each other, interact, form all kinds of different structures. And what we try to understand is to find the minimal recognition elements in nature. We are interested in, as was mentioned, molecular self-assembly, the way that molecules interact with one another to form ordered structures, self-assembly, they know each other to form ordered assemblies. Our approach is reductionist. We take complex molecules, cut them to smaller and smaller pieces, try to define really the smallest elements in nature that can form ordered structures. We extend it also to non-biological. We come from biology, but we extend it also to non-biological building blocks. And we can make all kinds of different structures at the nanoscale, including nanotubes, nanospheres, nanoplates, all the objects that we know from the macroscopic world, also in the nanoscopic one, in the very tiny structures. So I start with chemistry, and then we'll have some explanation that is less. So we are really interested in non-covalent interaction to form ordered structure. This is meaning those interactions, set of different forces that brings together one molecule to the other to form ordered structure. This is molecular recognition. Why one molecule recognizes a specific structure but not the other. It's a major field in chemistry, supramolecular chemistry. In our case, it's a little bit of supramolecular biochemistry, understanding those structures. As you see here, with all of you are familiar with Gulliver Travels, the reason that the citizens of Lilliput were able to bind Gulliver to the ground in spite of the difference in sizes are all these different little notes. And we are trying to understand and define in the molecular terms the different structures, and those different notes can bring together giant molecules to form a connection with one another. And so this is what we try to do. And we're able to identify various building blocks that can form this structure, ranging from structures large as viruses to things as small metabolites. And we use different techniques, peptide array analysis, spectroscopy, electron microscopy. We use animal models and high-resolution methods, all in all, to understand the way that these structures are being formed. And this is just a few highlights for the scientists in the audience of the things that we did recently. The Nature Communication paper in which we demonstrated the ability of different very small building blocks to form structures that are well ordered, can go to specific structures. And this is with large viruses. Again, the formation of a virus, and as you know from everyday life, the ability to invent and discover antiviral compounds is very challenging. And this is another way to look at self-assembly of ordered structures and interfere with the formation. One of the things that we've been interested in for many years was the formation of amyloid structures. These are self-assembled supramolecular structures. By now you know all these terms that are related to major human disorders, including Alzheimer's disease, Parkinson's disease, type 2 diabetes, and many more. We're able to, asking to understand the molecular basis for recognition. As we move with my 8 minutes, you understand more and more the terms. Molecular recognition that lead to the self-assembly of these ordered structures that are related to those diseases. And our approach is reductionist. We are trying to find smaller and smaller building blocks, and jumping for many years of work, we suggested how these structures are being formed. Some of you may remember it from their chemistry, high school chemistry, those aromatic structures, planar, hexagonal assemblies that are very rigid. We suggested for the first time a way to understand the formation of these structures, building a model of the way that these hexagonal structures are stacked one on top of the other to form these assemblies. Again, I'm doing quite a quantum jump, but something that was suggested by us based on theoretical methods was proven later on by high-resolution structure. This is from the University of Cambridge, and later on from Boston College. You can see here the way that these hexagonal structures are building one on top of the other to form these ordered structures. So we're able to suggest a new model to understand the formation of these structures. Understanding how these structures are being formed, we are now developing ways to inhibit the formation, that is the development of new drugs. And even without understanding chemistry, as you see the structure here in the lower right panel. You have the recognition of the hexagonal structure on the one hand. You cannot further allow the growth of the structure because of this steric hindrance, what you see here, like the two hands of the molecules. So this is chemistry in a nutshell, but we're able to identify. And again, in a little bit of a more later term, you see this formation of the structures, the ability. We are trying to make something like a Lego building blocks, but without the little chupchiks on the top of them as those structures. In the 1 minute that I still have, how we move from this to other structures. By going to smaller and smaller assemblies, we're able to identify smallest building blocks that can form all the structures like these nanotubes, published in Science already some years ago, making spherical structures. And by going to the smallest recognition elements, we're able to identify unique physical properties. So by molecular self-assembly, we can get things that are as strong, as rigid as steel, that have piezoelectric properties. You imply force and you get electric power. We see the semiconductivity properties of these structures, get luminescence of these structures. Again, in the 1 minute I cannot get into, but these have all kinds of different applications. Some of them were already applied by commercial, both established companies as well as startup companies. Recently, and this got some recognition by the general media, we're diversing also not only to peptide, but also to peptide nucleic acid, a convergence of DNA and peptides, getting all kinds of different diseases. Crystal structures for the chemist in the audience, of very unique structures that allow the stacking of the hexagonal structure on the one end, but Watson-Crick connection, as we see with DNA, for the others, and get also here, so all kinds of physical properties. It's very hard to get the message in 8 minutes, but I think if I have the 20 seconds. So we're interested in sociology of molecules, how molecules interact, how they form ordered structures. These structures have importance both in medical application, as in many degenerative disorders, these structures are being formed, and it could bring to all kind of technological application, because when you go to the smallest recognition modules, you get all kinds of new physics. This is of course, I'm speaking, but these people are doing the job, and one of the important missions of the Kadar family is to promote young scientists. So I would like to thank the university again, the Kadar family again, and thank you very much.